Okay, G. We are starting off with A2 Trigonometry, Lecture 2. Now, we have already covered the Lecture 1 with all the identities in the last class. A2 Trigonometry Lecture 1 included the identities. For you to understand that we went through the identities uh, till 10 to A. So let's just end the two, four remaining identities that were also there that you should be knowing before we start off with identity example questions. One thing that you should be knowing is that your sine square A is known as 1 minus cos square A. But sine square A, where needed, can also be written as 1 minus cos 2A upon 2. Now, this identity comes from the cos 2A concept where it says 1 minus 2A. So when we reshuffle 1 minus 2 sine square A to have the answer for sine square A, we end up having sine square A as 1 minus cos 2A upon 2. Similar way, we had cos square A as well. And cos square A was always taken as 1 minus sine square A. But in some conditions, you can always use cos square A as cos 2A plus 1 upon 2. So these were the identities that were left just to make sure that these identities are well versed with you guys. So let's just start off with example questions so that it gets easier for you to understand your trigonometry identity concept. Now let's just start off with question example number 1. Let's say that we have cot theta plus tan theta. Prove it to sec theta cosec theta. Now, with the respect to the identity, we know that cot theta is basically cos theta upon sin theta, and tan theta is sin theta upon cos theta. So if we just solve this, we get to know using the LCM method, sin theta cos theta will be cos square theta plus sin square theta. And sin square theta and cos square theta is basically 1 upon sin theta cos theta, because sin square theta cos square theta is 1. We already know that this from AS sin square theta plus cos square theta is basically 1. So we replaced this as 1. So now you understand that 1 upon sine theta and 1 upon cos theta can be used. Since 1 upon sine theta and 1 upon cos theta can be used, 1 upon sine theta can be shifted to what? Cosec theta. Whereas it can also be replaced with what? Sec theta as 1 upon cos. So we proved our example number 1. Let's move to example number 2. Let's say that we have 10 square theta plus we have cot square theta, and let's prove it to sec theta plus cosec square theta minus 2. So if we just prove this thing down, we can always say that 10 square theta, some of you might change this to sine square theta upon cos square theta, but the identity of 10 square theta can also be written as sec square theta minus 1 plus cot square theta can be written as cosec square theta minus 1. Minus 1 becomes what? Minus 2. So this can be written as sec square theta plus cosec square theta minus 2. So hence it is proved. Let's go with example number 3. Example 3. if we say that sine A upon 1 plus cos A is identical to 1 minus cos A upon sine A. Now, here you need to understand something. You do not have any identity of sine A, you do not have any identity of 1 plus cos A. Similarly, if I shift my right to left, sine A, 1 minus cos A does not have any identity. So that means nothing can be changed in respect to the identities that are there. But I can see one thing, that if I use 1 plus cos A, and in the answer we have 1 minus cos A. So the concept of rationalization can be used here. When I say concept of rationalization, that means sine A upon 1 plus cos A can be multiplied with the numerator and denominator. When you introduce something in numerator, you can always introduce that in the denominator as well. So what we can say is this can be 1 minus cos A upon 1 minus cos A, because since the identity here states that we need to have 1 minus cos, we need to have 1 minus cos A in the numerator. So 1 plus cos A, to change to 1 plus cos A, we have to introduce 1 minus cos A to make sure that obviously 1 minus cos A can come in the numerator. So now here what we can have is sine A, 1 minus cos A, and this thing can be 1 minus cos A and 1 plus cos A. Remember that we have an identity of A square minus B square as A plus B and A minus B. So when we have this identity, so we can easily say that we can use this identity as the following. Now let's just work it out through this. Let's say that sine A, we can use it in this way, sine A 1 minus cos A, whereas 1 square minus cos square A. We can reshuffle it to the same A square minus B square. So this is 1 square minus cos square A. Now 1 square minus cos square A is basically what? Is basically sine A 1 minus cos A. Now this can be sine square A. So considering that square and sine is cancelled, what are you left with? You're left with 1 minus cos A upon sine A. And this is what you had to prove in the earlier example part. So remember that such identity A square minus B square, A plus B, A minus B can be used. Let's move to example number 3. Your example number 3 says that example 3. Now let's just work it out in this way, that sine A upon 1 minus cos A plus 1 plus cos A upon sine A is identical to 2 upon sine A. 2 upon sine A. So the best way to solve such question is that when you see that there's nothing in the numerator that can be changed, nothing in the denominator that can be changed, and the same nothing can be changed here. So we can take the LCM easily. We can take the LCM easily. So to take the LCM, what we need to do is we need to understand that 1 minus cos A and sine A will be the denominator. This should be sine square A plus, whereas 1 plus cos A, we have a change in quotient. This is 1 plus cos A. So let's just have 1 plus cos A, correcting it down. Now let's just say that we have 1 plus cos A, so we can always write this as 1 plus cos A whole square. Now when we have this, we can write this as sine square A plus 1 plus 2 cos A, whereas we have cos square A upon 1 plus cos A, and this will be sin A. Now, moving forward, your identity sin square A, cos square A, when we use them together, we will always have this as 1. So if we just write down 1 in place of sin square A, cos square A, 1 plus 2 cos A, this can be written as 1 plus cos A and sin A. Can we have 1 plus 1 is 2? So 2 plus 2 cos A upon 1 plus cos A and sin A. We can always take 2 as common. So we have 1 plus cos A upon 1 plus cos A, and we have what? Sin A. Now we can see that 1 plus cos A, 1 plus cos A is in the denominator and in the numerator. So what are we left with? We are left with 2 upon sin A. So particularly this will be the identity that we had to prove prove initially when we were told that sin A upon 1 plus cos A plus 1 plus cos A upon sin A is identical to 2 upon sin A. Okay, the example number 5. So example 5 says that we have sec square A, which is identical to cosec A upon cosec A minus sin A. So what we can say is that sec square A does not have any much to do in it. So what we can do is we can always shift the right hand side to the left hand side as well. So we can write this thing as cosec A divided by cosec A minus sin A. So this cosec A now can be written as 1 upon sin A divided by, we can solve this in the bracket. So 1 upon sin A cosec A, which means we have this negative sin A. So if we take the LCM on the right hand side, so what we can see is 1 upon sin A, we can have divide because this is, we are just solving the right hand side bracket at the moment. So what we can do is take down the LCM, which will be sin A, 1 minus sin square A, right? So now 1 upon sin A with the mathematical rule, what we can have is we can change division to multiplication. But for that, we need to reciprocal the right hand side fraction. This would be sine upon 1 minus sine square A. So sine and sine is cancelled out. So what are you left with? You're left with 1. This 1 minus cos A, remember 1 minus sine square A can be written as cos square as well. So if we are changing this thing, we can change it directly. This should be 1 upon cos square A, which is identical to sec square A. So this is what we actually wanted. We wanted to shift from left to right, but we shifted the right hand side values to the left hand side in the given example. The next example, example number 6. What I would want you to do is pause the video here so that you can just solve this and then you can play the video. The question that we can have is, we have is 10 square A plus cos square A upon sin A plus sec A, which can be written as sec A minus sin A. So here's the question. This is example number 6. I would want you to pause the video for a while so that you can solve this thing down and then play it. Okay, so I guess we must be back. So example number 6. So let's just solve this. 10 square A can be written as your sec square A minus 1. And cos square A can be written as 1 minus sine square A. Now upon sine A plus sec A. Now what we can see is this minus 1 and this plus 1. Minus 1 plus 1 is cancelled out. So what are you left with? You're left with just the sec square A minus sine square A upon sine A plus sec A. But now, considering what we have here is, we can see A square minus B square property again, which is A minus B or and A plus B. So this can be opened as sec A minus sine A and sec A plus sine A. So if we just open this thing as the same what I have just written up, so this should be sec A minus sine A and sec A plus sine A upon what? Sine A plus sec A. So we just opened it through the formula that was there. Now let's just solve this thing a bit. We can see that sine A plus sec A and sine A plus sec A can be cancelled out. So what are we left with? We are just left with sec A minus sine A. And this is what we had to prove in example number 6. We had to prove that your tan square A plus cos square A upon sine A plus sec A is identical to sec A minus sine A. So this was example number 6.